Okay, I don't recall recording this session, but apparently it's recording. I forgot to set up recording, but it's recording. Maybe they enabled it by default. I asked them to do that. Maybe they fixed it. Yeah, I know it's recording. I just don't know how it's recording. I don't recall doing it, but I did ask the people there to turn it on automatically. Maybe they figured out a way to do it, because often we forget. Oh, there you go. The GA did it. I was kind of thinking that maybe it was possible for him to do it. Okay, so far 64 responses, still looking for about 8 people. I did turn on, or I did start the class with the polling system a couple minutes before. I don't know if you guys noticed that. I don't know if it sends messages to your phone or anything like that when I do that. Okay, 66 people. Well, I don't want to sit here. It does not. Well, there might be a way to turn it on to do that. I don't know if it has a notification setting. Okay, I'm not going to wait too long here. It is, well, almost 10:05. Great way to waste time in the morning. Okay, well, I guess we'll move on. For those, that's quite the autocorrect error. Yeah, I'll end at 3 minutes just because we can't sit here forever. Okay, I hope everyone's got their information in. Okay. All right, well, there's no reason for me to look at the results there. Okay, so I'm just going to move on to slide 12 where we were at the other day. So first of all, if there's any questions, again, you guys just please throw them in the chat. Again, please avoid doing private chats, just because it's difficult for me to kind of access that information. If you have something in particular to tell me that you don't want other people to see, just send me an email or something and I'll get to it eventually. But I do have multiple monitors here, but it doesn't show me all the chat threads. It just shows me the main one. I have to actually kind of go around and fool around for it to show me that information. Oh, what do I mean by private chat? You can actually send people particular messages directly. You don't have to have it in the public forum as you're seeing by default. I would not recommend sending anything terribly sensitive or anything like that because all of this information is being recorded. Not necessarily that other people can see it. It's just that what you might be saying to your friend is, I can see and the GA can see. So just warning you. Okay, so continuing onward. Just to let you know, I am working on a first assignment. This is outside of my normal curriculum for this course. Again, just things to give me more marks to kind of pull up in lieu of the exams. So it should be ready by 1 o'clock. I'm just checking it over, making sure it's all good. Everyone has a different one. It's basically just a number conversion assignment. It shouldn't take terribly long for most of you, especially if, again, my assumption is you'll pretty much use tools to kind of do the conversion to some degree anyway. Yeah, you would send everything back to me in a text file. Basically, you put all your answers there, and hopefully, because everyone has relatively random questions, at least the values for the questions are random, I should say. I'll be using a computer to do the marking essentially, so it should go pretty easy for everybody. Okay, so the other day I was talking about read-only memories, and again, these are just effectively memory devices where they're not only read-only memories, they're just harder to write to, we'll say. They don't write within the same amount of time we could read from them, is really their definition. So I kind of gave an example here of, a pretty simple ROM type device where we have 16 words. So we can see A3 to A0 as our inputs. It has an 8-bit output, so we see D7 to D0, and again, that's what our circuit would want to see, ones and zeros, because we're always using these switches that respond to that. But from a human perspective, we can kind of translate everything like that into a simple table of saying, okay, rather than write everything out in binary, we'll use either decimal or hexadecimal here, and we can see the output here in, well, this is hexadecimal, but it could also be in decimal, again, if the numbers are pertain to an application where decimal is more attractive to see for a human. Again, it all depends on what your application is. What are we going to use these numbers for? Okay, so this was the last slide I ended on. Here's our next slide here. So again, these devices, we're not going to get into how they're actually built. They're, you know, pretty complex devices from the perspective of learning. You know, when you go out and buy anything, I mean, the manufacturers are trying to make things as cheap as possible. So they're going to take whatever, I don't want to say shortcut, but any way that they can, you know, again, reduce costs. And there's a lot of things we can do in electronics to kind of get away with that, but they're not necessarily easily understood. So this picture here is just a functional diagram. Let me move this little thing here so you can see all the outputs. There we go. So we can see this is a 16x8 ROM. So each one of these registers here is an 8-bit register, so to speak. Now we'll just assume this is a read-only register. So it has something pre-programmed in and it's on, you know, forever, essentially. Its contents are always there. So we can see they're all connected on a common bus. It's an 8-bit bus. We can see that little 8 here. So only one of these things can write to this bus at once, or else we're going to have some kind of contention. So we need some way to turn these things on. Okay, so they output on this bus. Now we could use a 4 to 16 decoder, which would give me 16 outputs to each one of these registers. But a 4 to 16 decoder is actually quite large. So we have a thing, we talked about this in DLD1 called coincidence decoding, which is basically where you can use two separate decoders. So A0 through A1 go through one decoder, and A2 and A3 go to another decoder. And these are smaller decoders, a 2 to 4 decoder. And what's kind of important about this is a 2 to 4 decoder. Let's say its size, we'll just use like 1 unit. So a 3 to 8 decoder is going to be at least 2 units in size, and a 4 to 16 decoder is going to be 4 units in size. So a single 4 to 16 decoder, being 4 units in size, is certainly much larger than two to 4 decoders. So this is kind of the preferred method. Now, of course, there's other tricks we use in the real world, but this is kind of the way it's done. So each register, therefore, has 2 enable lines on it. So when both are active, then it outputs to the bus. So if A0 and A1 are both 0, output 0 is going to be a 1. This is going to be active. So all of these will have one of their enable signals on. Okay. And then when A2 to A3, for example, is 0, this output line is active. So this whole column has these outputs, or one of the other enable on, I should say. So the one that has both enables on, which will be this one here, that's going to be element 0, which is what you'll get when all 3 of the inputs are 0. And that one's going to output on the bus. Okay, so by using 2 decoders, it kind of makes more sense because we're kind of on, again, when we build our semiconductors, they are on a flat plane. We can't build transistors on top of each other. So we need a way to kind of say, okay, well, how do I turn on which transistor, so to speak, in this plane? So it kind of works well that way. Now it's possible to add, you know, more decoders, but you kind of have to say, okay, well, what is that going to control? So in real world memory, you know, another decoder might be used to activate a different bank of memory. So we might have an array of these 2x2 chunks of memory, and we just kind of say, well, which one of these arrays do we turn on? And it kind of makes it a little bit easier to manage. Now, do keep in mind that when you go and buy a memory chip, we're not talking a few bytes as we are seeing here, right? With this is a 16x8. They can be in the gigabytes of memory. So there's certainly a lot of words in there, and we have to be able to you know, to kind of access them and say which one is going on at once. And this is what really slows down memory. This is why DRAM is kind of slow. The speed of DRAM goes down as the capacity increases, because we have to figure out again, well, where is it? Where is that thing you want to read and write from? And that's what takes the longest time. Okay. All right. So again, we're not going to actually show you the insides of them, but we will talk about the different types of ROMs. So again, this kind of just, the slides here kind of just explain what I did. Just again, talking about the different address decoders, which ones go on. So we're basically taking the address word, which in this case is 4 bits, and we're breaking it up into 2 separate decoders. And again, if we use banks and or even other levels of breaking the memory up into some way, you'd use more decoders there. And again, this is kind of how modern day memory works. We have many different stages of memory decoding to kind of simplify this idea of finding out where the actual information is. And again, our memory will have some type of output buffer here on the end. You can see a chip select here. So even though I could be implanting different addresses here, and internally it might be saying, okay, well, I'm activating this one, or I'm activating this one, or I'm activating this one, nothing will go out unless the chip enable or chip select line is asserted. And again, this makes sense if we have our shared buses. So I could have multiple memories connected to our data bus, and it's just a matter of me selecting which one goes on at what time. So that's usually the job of the CPU to, again, arbitrate who is talking on the bus at what moment. And we'll get into that later when we talk about memory decoding strategies. Okay, now again, ROMs don't normally have to be very large because, again, we don't usually have that much code, so to speak. So you won't see these things, in very large capacity. So sometimes, 32 bytes to 1 megabyte. Again, they have very particular applications. For example, starting up a system, your cell phone has a boot ROM in it that basically, again, transfers control to maybe some kind of flash memory after. You don't want the boot ROM to be vulnerable to, invalid changes or accidental changes, because then the system just won't work. And again, with the way electronics are built today, they're not really made to be serviced. So it's possible that, a bad, upgrade to a device leading to a bad boot ROM would just, again, make it completely unusable, and there's not much point in fixing it. If you have to, unsolder chips to fix it, that's a lot of labor. I want to ask the question: when memory is stored, is it encrypted to store non-sequentially? Encrypting things in memory is a difficult thing to kind of do. Data encryption, there's different ways of doing this. It certainly is possible for you to try to scramble things in memory or scramble accesses and things like that, but at some point there's a core part to the system where memory has to operate as quickly as possible. So in my experience, when I've seen encrypted memory systems, they're not usually fast memory systems. They're usually kind of like a secondary storage system. I can give you a great example. If anyone has a Nintendo Switch, you have those little memory cards. The transactions between those things are not just, okay, go get memory at this address, okay, get the response. It's an actual transaction system where it sends out challenge response things, which are typically seen in encryption. Now it can do that simply because it doesn't really care about the speed. So if you have a Nintendo Switch and you go to play a game and you start it up, it doesn't start instantly. There's if you're in between different parts of the game, there's like loading screens and things like that telling you to please wait. And that's because it's accessing stuff off that card, and it's not coming in at full memory speeds. It's kind of more like a disk, and the system is it knows that, and that's why it kind of shows you like those little pictures or animations. So to kind of get that kind of performance, in terms of security, you have to kind of give up on speed. But for like real memory inside of a computer, like RAM, I know, there's AMD and Intel are talking about, encrypting memory and all these kinds of things. It might not be what we call strong encryption. It might be something, but you have to have some kind of faith in your hardware that it's in a relatively secured location. Otherwise, yeah, some guy can, pull out your server inside your server room and start sticking stuff in there and read out what's going on in your computer. I mean, there's a point where you just can't secure everything. Any case, where does the SSD fall in terms of memory and speed? Well, solid state drives are certainly fast. Don't get me wrong; they're faster than magnetic drives, but they're not as fast as memory. The memory inside your computer could be operating at 20 or 30 gigabytes per second. Your hard disk, you're just happy if you're getting 500 megabytes a second. I mean, that's pretty darn fast. So it's certainly by no means as fast as memory. And if it were ever to become that way, and well, I don't want to say it's getting there, but an SSD for most of us will have a SATA interface, but they have another interface. I believe it's called NVMe, which is a faster interface because SATA wasn't quick enough as these devices have gotten quicker. So we'll have to come up with faster ways to kind of integrate how we talk to these solid state drives and get them to kind of get information into the computer. And again, I'll talk about some of that stuff later on in the class, how we can move information faster. But again, it becomes more complicated, as it always does, right? To improve efficiency, you have to you got to be smarter about your design. Okay, moving on here. So with ROM timing, with any memory device, there's always a little bit of time before we get things out. Now, when I'm talking about these memory devices right now, I'm talking more about what we refer to as legacy memory devices. So these are asynchronous memory devices. They're more traditional. Again, when we started out with building electronics, we were kind of always faced with the problem of, how do we make things functional and also make things cost effective? And these were all kinds of issues. And now we have better ways of doing this stuff. So there's better ways of interacting with these memories. But the one thing you'll notice with legacy memories, there's no clock to them. And that will kind of make interfacing with it a little bit more challenging. So we kind of have to look at these timing diagrams. So again, there's always some type of propagation delay whenever we're talking to circuits, right? They're not instantaneous access right now. Again, for us as humans watching a circuit do something, sure, it's fast, but if we sit there and we look at it on an oscilloscope, we can certainly see rise and fall, times and those types of things. So all memories have some type of delay associated with them. So ROMs are no different. So here's kind of our device. So here's our address input. So we're just going to assume, okay, once I change this input, now again, these are asynchronous devices. So there's kind of a timing circuit built into the memory. We don't see it, but it is there. That kind of sits there and says, okay, you change the input address. Okay, so when does that kind of stabilize? So it's looking for when are you not changing it again? And based after so much time, it's going to kind of start beginning its operation. So we won't talk about how that circuit works. We'll just assume that it happens. So the circuit's going to realize that you've changed the address, and it's going to kind of wait around a little bit and see, okay, once you put in the address, I'm going to start hunting down that place in memory. So again, this is a ROM. We're trying to find the place to read. And it's also going to look at our chip select line. Now, our chip select line, this is really just usually connected to the output tri-state buffers. However, again, to save some power in some of these designs, they might actually connect this to the decoding logic as well. It's possible. So once we stabilize our inputs, our address inputs here, and you can tell by this the X here means it's kind of unknown. It can be anything. So once we see that it's like this, so clearly it's not a 1 or a 0, but this does imply that it's stable. After a certain amount of time after that stability, which we call time access, we should start getting outputs. And after a certain amount of time before we would get those outputs, it's telling us how much time we need for the chip select line to kind of actually enable. Now, again, these numbers here, I don't have any numbers here per se, but you would find those things in data sheets when you purchase memory or when you're designing with it. So we can see there's a certain amount of time, which the access time, before we get valid data output. Now, if it's too long, let's say this access time is longer, this is obviously going to be pushed back, and there's going to be this kind of region over here where it says high Z. Now, again, high Z means high impedance, but it doesn't necessarily mean if I try to read that line, I'm not going to see something. I'll see something. It just will likely be garbage. So if I have a circuit that says, okay, I put the information in at this point and I'm going to read it at this point, but let's say my memory is a little slower and it doesn't start giving out data until about this point. Okay, well, what am I going to end up reading? And you're just going to get garbage. You're going to get something. It'll be some pattern of ones and zeros, but it won't be consistent. And again, this is why RAM timing, and when I say RAM timing, I mean random access memory timing, consistent timing is important because we're dealing with a circuit. Memory devices, RAM devices, don't have a way of telling us that they're not ready. They're expected to be ready. They have to be ready. So when I give a piece of, a place to read from, and it's supposed to come back in that much time, it doesn't give a signal saying, I'm not ready, you're going to have to wait, something else is going on. It just doesn't work that way. Other devices like SAM devices, sequential access memories, do tell us that. They will give us some kind of feedback that, okay, the information isn't valid yet. In this particular case, we don't have that, right? So a solid state drive, as someone kind of mentioned before, we send a request to it and eventually comes back with a response, but it doesn't have to come back with a response for, I think the specification would probably say about 10 seconds before I start having an issue with it. Now, 10 seconds is a long time in a computer, but that's taking into account the consideration that, well, what if there's some kind of hard error on that disk? What if it can't read that part of the disk, or there's some kind of error recovery? And in fact, I think 10 seconds is kind of actually a short amount of time, really. That's usually what happens in server grade hard disks. For you guys and me, who buy consumer grade, it can take up to 2 minutes before it comes back and says there's a problem here. Again, because it's trying to read it, it's trying over and over again, right? It's trying to recover the data that you may be losing. So it's going to take more time. Whereas in server grade systems, 2 minutes, that's a long time. So they'll usually quit far sooner, because hopefully we have some other place where that data might be stored in some kind of redundant storage or something. Okay, so we do have to make sure we meet our access time. So if I do want to read information at this point here, let's say where my pointer is, and clearly that information isn't going to be ready, I really only have a few options. And one is either I slow down my circuit, so I reduce the clock speed so I can meet this timing here, or I just get faster memory. And slowing down a circuit is usually pretty easy. It doesn't cost much money, but getting faster memory can. It might be difficult to find. Okay, just because something's made doesn't mean you can necessarily get it. So the same thing applies to electronics, just like a few months ago when it was toilet paper. Sure, there's toilet paper in the world, but if someone else has it, you can't get it, or hand sanitizer, right? These are things that are in relative demand right now. The same thing happens with semiconductor chips. Just because someone builds it doesn't mean you can necessarily get it or get enough of them to use in your product. So sourcing parts is sometimes an issue in electronics, and we have to kind of, maybe make some compromises on what we can get versus what we want to get. Okay. ACC, or that's access time, and TOE is time to output enable. So again, this is telling me once I switch that chip select, how much time will it take before I see the output appear? Now again, don't assume the diagram is to scale here. This diagram kind of implies that TOE is about 3/4 of TACC, or T access. It's not necessarily. Again, timing diagrams are just there for reference. You really have to look at the numbers to make sure you meet the specification. So again, the access time is usually, it's well advertised in the part. It's usually right in the part number. So for example, if I buy a memory chip, it usually has a -10 after it, or -15. The 10 would mean 10 nanosecond access time, or 15 nanosecond access time, something like that. That's like the most important value, but the TOE may not be necessarily there. Can you flip it beforehand? You probably can, and the timing diagram would actually, or the timing data sheet would actually probably have some kind of, time between these two, or says, how often or how soon can you flip this with respect to the time. It's entirely possible. Now, again, this is the thing about these memory devices or legacy memory devices. There's a lot of parameters. Now, to simplify that, when we buy memory, now again, when we're buying memory, what are we buying, right? You're buying memory for your computer. If you look at the memory circuit there, you look at this memory module, you're going to see the memory chips on there, but you also see a smaller chip on there, and it's a little, actually, memory device itself. It's a separate one that actually has all the timing parameters stored inside. So when you plug it in your computer, it doesn't actually start talking to the memory directly. It talks to that little memory chip that has all the specifications stored in it. It pulls all that information out, and it knows how to talk to all the other parts of the memory. It knows all these parameters, so it can interact with it easier, right? It can kind of say, oh, it talks, these three different ways. Okay, I'll use one of those, right? Historically, we didn't have that. Again, that would have all cost more money. Now it's just, it's cheaper. It makes life easier, but we actually had to sit there and, I can tell you, when I had to add memory to my computer back in the early days, I had to sit there flipping dip switches and applying jumpers to kind of configure the memory speeds. It was certainly a lot harder. Like, this is why people didn't own a lot of computers back then. Like, we're talking early 90s, late 80s. They were not easy to configure. You had to buy them, and you had to have someone who knew what they were doing to kind of configure them. Now you just kind of plug in the memory, you turn it on, and it just works. But there's a whole lot of mechanisms that make all that happen. Okay, so I do have a clicker question coming up. Let's see what it looks like. Give me a moment to start the poll. Here we go. So if I wanted to build a 64 by 8 ROM, so 64 bytes ROM, what decoder configuration will minimize the circuit size? Okay, good. I see responses. That's what I want to see. Now, again, do keep in mind that every time we increase the size of a decoder by 1 bit on the input, we double its size, if not more so. So that's why we say it's exponentially scaled. We kind of have the same problem with multiplexers as well. So, I mean, these are great devices. Keep in mind, a multiplexer is built with a decoder, right? So the moment we add more select lines, we're basically adding a larger decoder inside. Now, normally in class, everyone would be talking and rumbling, but I guess maybe the good part about this online stuff is you guys can't collaborate that easily, I'll say. I'm sure some of you are still sending messages back and forth, or who knows what. And I don't want to spend 3 minutes on these questions if it's avoidable, I'll say. Again, 84, maybe 83 people in the class if you don't count me or the GA. So let's try to get those responses up there. Again, if you're not answering these questions, you're losing marks. If you're not answering them correctly, certainly you'll lose a mark, but if you're not even attempting, you'll lose even more. So if you don't know the answer, at least pick something. Can you give me a small hint? Well, again, if you assume, if you look at the smallest decoder, let's say a 1 to 2 decoder is 1 unit, and a 2 to 4 decoder is 2 units, just add it up, right? And a 3 to 8 decoder is 3 units, and a 4 to 16 decoder is, sorry, not 3 units for that one, 4 units, and a 4 to 16 decoder would be 8 units, and a 5 to 32 decoder would be 16 units. Find the one that when you use two of them, in what configuration gives you the smallest unit area. That would be the best thing I can suggest. And we're trying to go with the smallest area. Okay, someone says they can't seem to answer on their phone. I don't know if, I mean, based on past experiences, we certainly had people using phones before. The last time we had some kind of issue with their system. The browser seems to work quite well, so if you can use the browser, I might suggest using the browser more so, but your phone might have a data issue or a connection issue, I'm not sure. Okay, we're gonna come up on 4 minutes here. I wanna give you guys the most, or the greatest opportunity to answer, but at the same point, I can't sit here waiting 4 minutes per question. So I'll wait a little longer, 4 minute mark, and then we'll kind of move on here. Good, it worked. All right, so we're gonna stop here. Oh, someone just got it in. Oh, okay. So what do you guys think the answer was? Well, let's take a look. Well, it seems to be a cross between C and B. Well, the actual answer is, which one give the least? So if the 1 to 2 is 1 unit, and a 2 to 4 is 2 units, and a 3 to 8 is 4 units, then the best choice would be C, 2 of those. Let's go here, and there's my little star. And right now, because I clicked on the response here, it should update the database online already, so you already know what you got. Okay, so again, just looking at the results again. So if this is 1 unit, this is 2 units, this is 4 units, 8 units, 16 units, right? So 16 plus 1, that's 17. This would be 8 plus 2, that would be 6, right? So this would be 4 plus 4. No, not 8 plus 2. That's wrong, right? No, this one would still be too large. Again, I'm just making kind of just the idea that we want it to be as small as possible. So if we can use the smallest decoders, do people still want these to be 20%? Haha. Okay, so this is what we're going for, right? The smallest decoders possible. Okay, moving on here. Okay, now the different types of ROMs. Again, I hate when this thing is on top of my pictures. Okay, maybe I'll just bring it over here. Don't need my name to be seen over and over again. All right, so different types of ROMs. So again, originally when we were building ROMs, we didn't have the ability to program them per se. So we have what we call mass programmed ROMs, and these are ROMs that are built at the manufacturing facility. So as the semiconductor devices are being built, we're actually putting the actual pattern inside them. So the picture on the side kind of shows the idea of this. This is with bipolar transistors. The actual picture isn't really important. What it's showing is that, okay, we had some kind of decoder here, and each wire goes to this, this is like a 4-bit memory coming out. So we can see at this particular device here, there's a connection, and at this point here, there's no connection. So at the manufacturing time, they either remove the connection of the transistor or they completely eliminate the transistor entirely. So based on whatever address I put in, I will get a unique value out. Well, it doesn't have to be necessarily unique, but whatever the ROM pattern is, and there's no way to change it because the transistors are placed when they're manufactured. So this is certainly the best way to do it. The problem is it's very expensive because you're building a particular chip for your ROM. And when we build chips, building one chip at a time is not cost effective. It's actually really expensive. Whereas if I'm building, 100,000 of them, that's when it becomes cost effective. Okay, so whenever we build any type of chip, we have to have quantities at least of about 100,000 for it to be cost effective. So if your application, or if you're going to be selling at least that many, it makes sense to do this. It's going to be the most cost effective, right? It'll be cheaper in the end. Okay, so again, when they, build cell phones or things like that, they're they're certain to make sure that, okay, we're going to build more than 100,000 or whatever device it is. It's just common sense. So when I was, again, growing up and I had these devices, well, these computers, again, they had ROM chips in them, and the ROM chips, yeah, they were custom designed, right? It has that particular code in it, and you can't change it. And again, what's nice about it is no matter what you do to this thing, you know, it could screw up so badly. You know, the program could get confused so badly. There was no way that it was ever really going to kill the computer, because all you had to do is, okay, well, it's not working, turn it off, turn it on again, it's back to normal. It's just the way it worked, right? And again, as I talked about the Mars rover, when they had that situation where all the flash memory was erased, again, due to some cosmic radiation event, whatever it was, the ROMs didn't change because, well, the radiation couldn't add or remove a transistor. It was simply just there or it wasn't there, and that bit pattern was consistent. Okay, so this is certainly the best way, the most reliable way. However, again, it's costly. So unless I'm selling over 100,000 of whatever I'm building, it doesn't, you know, this makes sense, you know, whereas the other option doesn't. So how can we make this cheaper, but for lower quantities? And again, as time progressed, they came up with something called programmable ROMs, or PROMs. So these devices, basically, when they're built, they can contain a fuse. So if we kind of zoom in on this area here, we either put in a connection to the transistor or we didn't. And a PROM, we would see something more along the lines of this, where we see, you know, whatever device is being used to kind of control the bit pattern. Here we have a fusible link here. So right there, the fuses are all there, they're all working, everything is great. Now, when I program it, I basically apply a higher voltage to burn out a fuse if I don't want it. So let's say, for example, if you were to read the contents of a freshly made PROM, you would always see ones coming out of it. But if I wanted to change that 1 bit to a 0, I would apply a high voltage at a particular point in time, and it would blow out this fuse. So the fuse gets blown out, so now this transistor isn't connected, and now I would get a bit 0 there, for example. Okay, so we actually do this still in modern day circuits, where we do put in these fuses. So they're intentionally being blown so that, yeah, you can't access that point of the circuit. Again, a lot of devices do this today. We even do it in DRAM. Again, as I mentioned before, DRAM has extra memory, you know, to compensate for bad bits. Well, when they do that final testing to find out where are those bad bits and how do we kind of, you know, redivert that flow of information to an unused portion of the chip where we can, you know, recover those bits, they're basically blowing these fuses. There's, again, a special way of doing it. So to do this with PROMs, we have to program them with higher voltage circuits. Again, there's a process. It's not by any means, you know, absolutely simple, but it's certainly doable. Now, the problem with the PROM is, though, to add in this feature, well, it costs more money. So the per unit cost of the device is higher. But if you're only, like, again, making 10,000 of whatever you're building, you need 10,000 PROMs. That's far cheaper than going out and buying 100,000, you know, just mass program ROMs, right? So we use these based on, you know, what we need. They all do the same thing. They just cost different amounts of money. Now, once the PROM is programmed, that's it. It's done. You can't unprogram it. Okay. Well, what if we need to change the contents of the memory? Okay. So we've come up with something even newer called an erasable PROM, or an EPROM. Okay. Again, very similar to a PROM, but it can be erased. Now, I don't know if you guys have ever seen these before. You may have seen them. Usually there's a chip with a sticker on top here, but if you remove the sticker, you'll see a little glass window here. And the glass windows, I want to say it's kind of like a magnifying glass, but it's certainly a way of focusing light to the semiconductor device. And the semiconductor device, the bits are stored using what we call a floating gate. And to reset the floating gate, we apply a UV light source. So if I want to erase these devices, I have to put it in what we call an EPROM eraser, which is basically just you know, a little box essentially that applies UV light. And it's not instantaneous by any means. It usually has to sit there about an hour, but that UV light will erase it. So for example, an erased device has all ones in it. So when I read out the data pattern out of it, it will be all ones. But when I program it, all I can do is change a 1 to a 0. I can't change a 0 back to a 1 electrically. So an erasable PROM, and again, this is usually typically a higher voltage to change that gate. So it would again change a 1 to a 0. But if I ever want to go from a 0 back to a 1, I have to apply the UV light. And of course, I can't be arbitrary on which bit I'm going to set back to a 1. It does them all. Okay. So again, this was kind of like the next level. Now, again, these are more costly. Yes, they're all non-volatile. That sounds awful. It's not awful at all. It's the way technology progressed. Again, these cost more, but then again, I can reprogram them over and over and over again. And I still have these. I use them in old electronic devices. I have a programmer. I have my little UV, box that I put these things in to erase them, and it's good. It's better than having a PROM, because again, if you put the wrong pattern in a PROM, it's basically garbage, right? If it's not good. So again, I use these in applications where I'm constantly changing this, right? Okay. Now the next stage is, well, what if I don't want to wait? Yes, I do have to remove the circuit. So these would be socketed. Now they look just like this. They're DIP packages, right? DIP packages fit into breadboards, those types of things. So they're easily removed. But again, and we can get better sockets. There's different types of sockets out there, better quality sockets. The best quality you guys may have heard of is called a ZIF, zero insertion force socket. It's got like a little arm that squeezes the pins of the chip. But again, they cost more money. So if you're moving chips in and out a lot, you would use ZIF sockets to kind of hold them. It's again the better way of doing it. Now again, these chips are quite large. They do take up quite a bit of space. It's not like you'd be putting these in your cell phone or anything. But in any case, okay. So again, UV light to erase this. Now again, it all depends on which applications you need. So if you do have a device that might need the occasional device upgrade, and again, what was done historically was, if I needed a device upgrade, I would get a chip in the mail basically, and they would say, okay, here. Here's a new firmware upgrade. Just plug this chip in and go from there, right? That's what they would do. Again, most people didn't have EEPROM erasers back then. Someone was just asking me what's going on for the lab. May have came in a little bit later, but I might do a little bit of a lecture, but I'm certainly going to give out the first assignment and maybe give you guys some time to kind of like look it over and see if there's any questions. Okay. So what's the next evolution of PROMs at this point? You'll probably have 2 weeks to complete it. So we had erasable PROMs. Again, this is erasable through some external, again, you could call it radiation, right? UV light. Oh, another thing is, if you ever see these devices and there's not something covering the window, you should always cover the window, because especially if it's some old electronic device you intend to use, just by exposing it to the light in a room, there could be some UV components to that bulb, and it could start erasing just some arbitrary bit. So they should always be covered up. The windows here should always be covered up. Again, you never know what's on that device or whether or not it can be found, right? Can you find whatever pattern was programmed in that memory today if you had to, right? It might be very difficult. So okay, so the next evolution of these devices is something called an electrically erasable PROM, or a double EEPROM. We don't say EEPROM, we say double EEPROM, just like we say IEEE, because it's silly to say IEEE or whatever all the time, right? So double EEPROMs, or sometimes you'll see an E with a squared up here to imply you say it twice, and PROMs, for example. So again, this one uses a floating gate, but it can be reset by an external voltage instead of a UV light source. And that external voltage is usually the same as the supply voltage of the circuit. So for example, to program an EEPROM, I would usually need, like in a 5-volt system, I might need 12 volts, or to program a PROM, I might need 12 volts. But for an EEPROM, my circuit is operating at 5 volts normally, and I would just apply some, it'd still be operating at 5 volts to a rate, or to set. So with electrically or double EEPROMs, we just apply some kind of like write signal that just says, here, write to this place. So the circuit automatically erases it and writes to it for us. Now, again, it's not usually super fast. It's slower than the standard read cycle, but at least it can do it without any real special circuit modifications. Okay, so this is what we typically use now. Your motherboard, again, it's usually about cost. So they use flash memory, which I'm going to get to. Now, where an EEPROM is good is when you need to change very little things at once. EEPROMs are usually called NOR memories when we talk about them now in today's day and age. It's the idea of what NOR means. It just kind of says how it's built internally, like a NOR gate. So they're good if you want to make small changes. You know, I want to change a byte here, I want to change a byte there. So it's good in, you know, devices where you're just changing some setting here and there. So in your motherboard, this would be an EEPROM would be your CMOS settings. If you guys have ever heard of that term, I'm not even sure what CMOS means historically. So historically on motherboards, this was, you know, some setting that you could change. You know, like some kind of configuration aspect about it. Whereas the BIOS is usually stored in a flash memory device, which I'll get to, well, very shortly. So again, EEPROMs are good for, you know, small changes, but flash memory, now this is the latest and greatest stuff. This is the modern stuff. It's certainly smaller, it's faster. Because there's great demand for it, there's certainly been an initiative by the industry to make it smaller and faster. This is really what's pushing the technology when we see them trying to make transistors smaller and smaller. It's flash memory is one of the reasons. And again, all you guys own, I don't think it would be unrealistic for me to say almost a terabyte of flash memory easily. You know, once you start adding up all these you know, cards you have. So what's different about flash memory? Well, of course, it's modern. It can be cheaper just because of just the market, right? More people are selling it, more people buying it. Most people don't go out and buy EEPROMs. It just isn't the situation, right? But they buy flash memory. It's just what it is. Now, the major difference is that flash memory stores information in large chunks. So when we want to write to it, we have to erase a large chunk of it and then write back to it. So if you're using a flash memory card in your computer and you say, okay, well, I'm going to erase, or I'm going to just change 1 byte of a file, it actually has to go to that part of the file, erase the whole part of the file, and rewrite the new part of the file. So just by changing 1 byte, it basically has to read that file back, tell it to erase that part, and then take what it read back and alter that 1 byte and then rewrite everything back. So it's a larger transaction. So the block size, if I can say, to flash memory is usually 4K, 16K, maybe even larger. So that's what you have to erase. So you have to erase large chunks of memory to kind of utilize this. And it's the erasing that takes the most amount of time in flash memory. The programming, not so much. So writing to it isn't really what slows it down. It's erasing and writing to it. So unless you have wear leveling, which is a process where your flash memory device tries to even the writes to all portions of memory all the time, rather than, you know, just reading and writing to the same place over and over again. It tries to disperse that. You'll typically see that flash memory is slow. So again, if you guys have these micro SD cards, you'll note that the write speeds aren't really fast. They're not like, you know, solid state drive fast, right? Again, solid state memories or solid state drives are a compromise of, well, how do I get flash memory and speed? So they do a lot of stuff in parallel. They'll have parallel memory chips. They'll use a lot of wear leveling. The system is always trying to erase unused sectors so it can write to it faster. There's a whole, you know, song and dance going on behind the scenes to make them operate as fast as possible. But if you have just your little flash memory card, and you can see you're compromising on space for speed, right? You want to have a physically small device. You want to have a large space in this small device, but you don't want to spend a lot of money either. So what are you going to give up on, right? So speed is what it gives up on. So anyone that has, you know, like a USB memory stick or, you know, whatever, even if you buy a USB 3.0, you're not getting USB 3.0 speeds. You're still getting maybe 40, 50 megabytes a second at best write times. And you know, that's, don't get me wrong in saying it's not fast, but it's certainly not as fast as the memory can read from, right? So In any case, and just as a little tidbit of information, it's called flash memory because the person who designed it, or at least invented it, I suppose, noticed that there was it kind of emitted a small flash of light when it was being programmed or something, or erased. So that's why it's called flash memory. So the flash memory, again, going back to a question that was asked, this is where your BIOS is stored, the actual code, because it's pretty big. The BIOS in today's computers is much larger than it used to be. And you don't change it that often. It gets changed only rarely. And if you've ever done a flash memory upgrade on your computer, it certainly isn't fast. It takes some time, right? It's, it says, okay, don't touch your computer, don't remove the power, and it's not certainly by any means instantaneous. And I'm sure if you guys have updated the OS on your phones, that's not something that happens very fast either. It takes some time, right? So again, because we don't read and write to these things that often, or I should say write to them, it's a slower process. That's where the compromise is. Whereas solid state drives, we're always writing to them, so they go out of their way to kind of improve the performance. But you see that in the cost, right? A solid state disk is pretty expensive, compared to a flash or a micro SD card for the same size, right? Again, different operating speeds, different circuit sizes, and again, certainly a solid state drive is much larger than a micro SD card. There's no question about that. Okay. All right, let's move on here. So what are the different applications for ROM? Well, again, I kind of mentioned one of them, firmware, which is something you often hear. And it's basically the operational code for some type of embedded microprocessor. And it's called firmware because it means it's firmly stored in the ROM. So it's not changing often. So firmware is the term we use for just about any device other than a computer, which we then call BIOS, right? Because again, the computer BIOS again stands for basic input output system, whereas firmware, it's kind of more a generic term. So again, when you turn on your microprocessor, it knows that once it gets turned on and it's been reset, it's going to go jump to some place in memory and start running that code. That place in memory it jumps to is going to be mapped to this ROM, where it's going to read that information and start executing code. Now, another version of firmware is something called a bootstrap. And a bootstrap is basically, it's the initial code that enables the CPU to move on to the next phase. So again, in your computer, the BIOS basically tells the computer what to do when it turns on, how to do all of its tests, and it tells it how to load the operating system off of a hard disk. But you certainly by no means have an operating system on your computer. It's relatively useless without the operating system. And again, the operating system is far larger than the the flash memory or the ROM capacity. So it's usually a way of getting to the next stage. Again, your cell phones have this. It's a way of the boot up code that then transfers it to load the larger operating system. And another great use of ROMs is for some type of data table. Again, sometimes data it's too computationally difficult to generate, right? It just takes too much time, or again, it might be difficult to actually do. So it's better just to put it into a table. I can give you a great example of this. If you ever bought a greeting card at the store where, when you open it up and it starts playing music. Well, this is basically the circuit that does that. So you basically have some kind of counter that resets every time you open up the card. It gives an address to a ROM, and that ROM outputs the data, which is actually the waveform. And that waveform goes to a D to A converter, which converts the digital information to analog, and it connects to a speaker that plays that song. Now, if you guys have ever heard these cards, now this is the one that actually plays an actual recording. The audio quality isn't great because, again, they're compromising on, the sampling rate, so it's going to sound not as good, and they're also compromising on the precision of the signal, which again affects the performance, right? Now, you may have also heard the ones that play like tunes. So again, where's the tune coming from? Again, the tune could be in a ROM, and it's just passing that information to some kind of synthesizer circuit that generates, the different notes to play whatever song is being played. I've even seen some of these cards where you can actually record the message that will be played. And again, that's just an application of using a PROM in that situation. So Again, data tables, I often do this, again, when programming older devices that are much slower and they can't generate the data in time. I use data tables, not necessarily in a ROM, but maybe in a software situation where it's just faster to do it that way, right? We have to make compromises somewhere. So again, you'll give up on space to hold this table because you don't necessarily have the speed to generate it, for example. Okay, so I do have another clicker question coming up here. Let's go to it, and I will start the poll. Okay, I think this one is pretty easy. I think you guys should be able to answer it fast. This is a gimme mark. Not a hard one. I hope the rate of the responses here is due to network issues and not the time it takes for people to answer. Now, I would assume you guys do have access to the slides as I'm doing this. So you could just kind of flip back and just do some basic arithmetic. But if you don't, no, the ones we discussed, which is really the number that are actually out there today. We only have those 5 types. Ah. You know, I was trying to avoid that so badly. Oh well, I knew it was going to happen eventually. Nuts. Okay, we'll get your answers in. Darn it. Okay, I'm stopping it there. Do I even need to do this? Well, some people didn't get the hint, so it is actually 5. Okay, it is 5 types. So whoever picked B there, well, maybe you shouldn't have got up and walked away for a little bit. Does make me wonder how people are actually listening, or is anyone out there like, you know, listening to this with, you know, a headphone in their ear, listening to some music on the side? I don't know. Okay, so the answer is, of course, 5. Oh, another question. Here we go. All right, I'm not going to give this one away, that's for sure. If you need to have software write a single byte to an internal PROM device once a day, which device type would you use? I'm going to sit back and not say anything. One of the devices we talked about. Now, don't read into the term that I said in internal PROM once a day. Not saying that it's necessarily B. I'm just saying in general a programmable ROM device. So all of these are considered to be one of those. It's in that category per se. Okay, please try to get your answers in soon. So one thing I hate about the clickers, it just takes so much time. But what else do we have to do, right? Okay, come on, get them in. We're going to be ending it very soon. All right. You guys are killing me. All right, there's only going to be 86. All right, so what do you guys think the answer was? Let's take a look here. Everyone is going with D and EEPROM. And yes, the answer is D. So I'll tag that as being correct. And yes, so the double EEPROM is a device used to do just changes, small changes. Again, in an embedded device, we simply say, here's the address, here's the data I want to write, go ahead. And it certainly takes time, more than a single read cycle, but it'll get the job done. Now, I could also use Flash. Now, options A to C couldn't be done in software. You need some kind of hardware or some kind of hardware mechanism to do that, right? Obviously, the first one is no good. That would have to be done in manufacturing. B, it can only be changed once and then it's done. And C would require, the UV light source to kind of be applied. And I suppose, is it entirely possible you could build a whole circuit that does it in C? Maybe, but it would be extremely unlikely. And E, although possible, this would obliterate more than one byte. It would take out a lot of information. So you'd have to reprogram all that information over and over again, and that would be kind of a waste. All right. So it is D. Okay, let's move on to our semiconductor RAMs. Now, when I'm using RAMs here, I'm of course talking about read-write memory. But our term has always been RAMs. So you're never going to avoid it. It's just the way it is. So we'll use the term RAM to describe them. So again, RAMs are random access memory. So the access to everything I'm talking about here basically is random access memory, but the access is consistent. They're used for temporary storage. So when the power is removed, the contents are lost. Now it's very fast compared to other storage systems. And when I say other storage systems, any auxiliary storage system, hard disk, solid state disks, whatever, tape, optical, right? So if we do need to preserve their contents, there's usually some type of standby mode to do that. And again, that's where we only power the memory system to kind of remember that, and we can kind of turn everything else pretty much off, right? Again, most of our circuits are what we call static, in the sense that if I'm not changing the clock, it preserves its current value. So SRAM circuits, flip-flops, these are all static. DRAMs, again, being dynamic, they will lose their contents if we don't actively do something to keep them going. Okay. So I did talk about this the other day. So again, RAMs are, again, far more complex than ROMs, generally because, again, the refresh circuits that we have to put in. So again, we're just looking at very simplified block models here. So this diagram isn't much different than what I showed you with the ROM. Here, we're showing you a very large decoder to get to all 16. This is 16 by 4 memory. So again, we put in our address. One of these lines is asserted, and that tells one of these registers to either output or take information from our input. Sir, do you know how on the motherboard of the computer there's always a little battery that keeps... Okay, so that battery is for, again, I talked about this CMOS device that kind of, it's like an EEPROM that keeps certain settings. It's also to run the onboard clock. So again, when desktop computers were being built, this circuit is kind of a compromise. It's more like a powered RAM than an EEPROM, I should say, because it keeps the clock running and it keeps these settings. Now, again, what the rationale was for the design could have simply been when the people who designed the IBM PC, which were just some guys literally on a side project doing this at IBM years ago, they just probably just found some part that just kind of met their need, so, by some manufacturer, and that became, the basis for this. But you'll still kind of actually see that today, which is kind of amazing. But I don't know if it's done on purpose. Like if you don't turn on a computer after quite a bit of time, it'll come up and it'll say, "Oh, the time is wrong, and all the settings have been set to default," and you'll see terms like that thrown out. But the good part is the batteries are um, they're usually often rechargeable to some degree in these CMOS devices. So again, depending on the who built it, the function is the same, but I've seen it where the batteries are sometimes rechargeable. In other cases, you have to replace the battery because again, it's the cheaper option. If you're buying a desktop computer, they usually go with the battery because it's easily serviceable. But if it's a laptop, they might go with something else, right? I'm not saying RAM was an accident. No. No, RAM was intentional. In fact, there's even earlier memory. I'm talking about semiconductor memory here. I had one of our past technicians had a display board of different storage, and he actually had magnetic core memory, which was just amazing when you looked at it. It was just this array of little magnetic cores, and that's how they would store memory, using magnetic cores. So again, someone asked, what is WE and RW? So WE is usually write enable, RW is read write. So this kind of dictates the mode of the system. Now again, this is just a functional diagram using just basic gates here. So we can see this is an AND gate with inverted inputs, right? It's just to kind of show the way it kind of works. So if we look here, for the information to come into here, into these registers, read write has to be a 1 for read, right? So when we write R/W, what we're really saying is the read is low the read is high and the write is low, right? And the chip select also kind of plays a role here. So if the chip isn't asserted and you're trying to do a read or a write to it, it won't write, for example. That could be used as a memory enable. And the same thing out here on the bus, right? If the chip select isn't set on, or if you're not doing a read, it's not going to output anything. Again, with legacy memories, there's all different types of configurations. So you kind of have to find what you're looking for to meet your application. Now, with today's more modern memory, there's standardized interfaces and operating modes. So that way, you're not stuck to a particular vendor if you when you design your chip. So in case you can't source parts from one vendor, you can switch to another vendor, and the part is functionally identical. It's the same packaging, it's the same pinouts, everything like that. So that's at least one good thing that's happened in the memory industry, is they all got together and kind of came up with these standards. So it's not unusual for you to look inside your computer and you see your different memory modules, and you could see different chips on there and different chips on each module, or even different chips on the device itself, because they all have to meet some specification to kind of be there, so to speak. So okay, so again, in any case, it's not much different from a ROM, except we can write to it, essentially, right? Now, the one issue with RAMs, because they usually typically have higher capacity, so these registers that store the information are usually much smaller, so we can have larger and larger capacities. So the number of pins going into these devices ends up getting larger. So they try to kind of go out of their way to reduce the number of pins, because this impacts the size of the device. You could have a very small semiconductor part, but if it has a lot of pins on it, you're going to need a larger packaging for it. And packaging costs money. The more pins you put on a chip, the more it costs. So they try to cut things down in that way, while still maintaining proper operation. And I believe I have a slide on that later. But that's for DRAM. So for SRAM, they don't necessarily try to cut down on it because they're more concerned about speed and performance. But we'll talk about that soon. So as far as the operations go, they only have two operations, of course, read and write. The basic way this works is we for most part, they're pretty much the same between both. We set the address, we set the read-write mode. Am I doing a read or a write? And I set the chip select mode appropriately. Do I want the output to appear on the bus? Do I not want the output to appear on the bus? And then for a read, we would wait so long to get the information out. And for a write operation, we would also apply the data, and we would have to wait so long again for the information to be committed. We can't just say, okay, here's the information to write and let's move on to the next one. If you change the data that's supposed to be written during the write operation, it will most likely be corrupted. We have to make sure we meet the timing specifications. And I'll show you like a slide that's kind of an example of that. Okay. Now, as far as static RAM goes, again, this is certainly the memory we would like to use. And basically, static RAM is essentially two flip-flops back to back. Or I should say it's essentially two inverters back to back. I'll draw a little picture of it on the screen here. But so depending on the technology that it's built on, and again, these are older technologies. So with bipolar transistors, this would have been a memory or a static memory cell. You can see the output of one connects to the input of the other. Here's the output, it connects to the input of the other, the output connects to the input of this one. This one is an NMOS circuit, and NMOS means we can only build things with NMOS transistors. There were no PMOS at the time, or we couldn't build the PMOS and the NMOS together on the same wafer. So again, same thing, the output connects back to the input, the output connects back to the input. So it's this stable state. Now for CMOS, again, this is the more standardized design approach. Same thing. This is an inverter. This is an inverter. Over here, we don't see the how we're facilitating how we do a write to the memory cell, but here we do. M5 and M6 are kind of responsible for the writes. So when these are enabled, we're able to change the value of these cells. So just give me a second here, and I'll switch to whiteboard mode. All right, and of course, that didn't work. 1 second. Try again. Put on my pen. For some reason, I gotta. So a typical memory cell would look something like this. So here's my inverter. Here's my other inverter. Well, that's great. That's not what inverters look like. Not really thinking much while I'm drawing this, am I? There's my other inverter, and it kind of looks like this. So if this is a 1, this will be a 0, right? And if this is a 0, this will be a 1. So it's in harmony, right? Nothing is changing. The circuit's not switching. It's never switching. It's constantly static, and therefore we call it static memory. Now, if I want to change this, here's where the little bit of problem comes up. What if I want to change this to a 0? Or let's say this is the output. This is what I'm actually reading. This is my output. Okay. If I want to change the output to a 1, for example, I have to make this a 1. How do I make this a 1? Well, I have to make this a 0. But there's a chance that when I make this a 0, the 0 that's still driving here might force that 0 to go back to a 1, and nothing will actually change. So that's why we put in these pass transistors here, which I showed you before. This was M5 and M6, essentially. I think this was like M6 and this was M5. So if I want to switch the state, I have to put a 0 here, I have to put a 1 here. So I actually have to update both sides before I do it. So if I assert M5 and M6, it allows this 0 to pass through, it allows this 1 to pass through, and I've changed the bit. So that's why we need those two transistors on the side to kind of change the bit of memory. But we can see it's a very static thing. Once it's changed and M5 and M6 are off, we have that, again, harmony where the system isn't changing anymore, right? So the circuit is static. So as long as power is applied, the circuit operates, right? And the nice part is there's no change in the operation, so it's relatively low power. So it's very fast to update, and once we update it, we can sit back and just leave it alone, and everything is fine. That's what we like about SRAM. What if you have only one transistor instead of 2? Well, these, like here, you mean? Like only M5, for example, instead of M6? Is that the question? Okay, so again, as I mentioned, if I don't have M6 and I try to set this to a 0, right? So this thing's going to output a 1, but there's already a 0 on this bus. There's a chance this 0 could kind of get through and keep this at a 1. So there'd be a contention here. So again, we don't want, again, you guys have to realize these transistors are very small. And remember, there's 2 transistors in here, there's 2 transistors in here. So it's not, oh, just because this is 0, it should automatically be able to override this. It may not be that simple, okay? So clearly, if this was possible to only do with 1 transistor, they would have done it. Yes, you can have a stronger transistor, but remember, a stronger transistor means a larger transistor. So if I make this bigger and I'm able to get rid of M6, I might end up making the whole circuit larger in general. So there's always compromises that are going on here. And again, in memory design, remember, we're trying to put these transistors as close together. I mean, I could show you some layouts of memory design and you'd see that the last thing they want to do ever is waste space. And if you see the way they lay them out, everything is almost like it's on top of itself. It's kind of actually crazy. Okay, so we do need those 2 transistors here. So when we say the CMOS memory cell has 6 transistors typically, so you got the 4 to hold the actual value and you have the 2 to actually change its value. So there would be a ton of these little loops in the memory devices. Yes, that's what an SRAM device is like. You just have these small circuits where there's these little loops. Yep. Okay. Now, if there's no other questions, now again, unfortunately, when I switch out of whiteboard mode, it erases my whiteboard. Again, I don't know why it does that. I could understand it doing that. You know, if I go to a new slide, I have a different whiteboard, but I didn't write PowerPoint. Okay. The nice part is I can actually mark up this screen, go back, and then come back here, and the markup is still there. It'll even save it in my PowerPoint file later, but it won't save the whiteboard. Funny enough, eh? Okay. So that's SRAM. So again, it's nice to use, but it comes at a cost, right? There's a lot of transistors there. It takes up some space, right? I have to pack 6 transistors essentially in the same space that I can pack, well, just, 1 transistor for DRAM. So obviously with DRAM, I can put in more transistors there and get more density. So CMOS is definitely well, it's the technology of choice now, the implementation technology, simply because it's lower power, faster speeds, all those types of things, right? And when everyone's working on it, everyone's competing to make it better, it's always going to reduce cost. So that's what people do now, right? Again, SRAM is used in very particular applications. I don't want to say we try not to use it, only because it just costs more money. We'd rather use DRAM and deal with the headaches of DRAM than using SRAM just because it lowers the cost. And that's the way life is, unfortunately, in design. Okay, I have a few more minutes here, so I'll just try to get through maybe this slide here. So again, SRAMs or our memories are usually directly connected to a CPU controller to maximize efficiency. Again, the CPU is always doing memory transactions. So here's a typical diagram you would see with a legacy memory, like a timing diagram. We would see our input addresses. Again, this is the moment I would change my input address. So again, there's an internal circuit that generates all the timing signals for this. So once it realizes that my addresses are settled, it starts the operation. So what we kind of saw before with the ROM, we had the access time here, and we had the, well, this was TOE before, and now it's called TCO. This is the time for the outputs to become active, right? So this is my chip select just before, like on a ROM, but now we have TOD, the time the outputs remain active. There might be a moment here that that the output is no longer valid because I'm changing the inputs again, right? That, for example. So again, this is by no means drawn to scale. It's just kind of to try to give you that idea. So the access time is usually the amount of time it takes from when I change the inputs to when the data is valid. But if I change the CS signal, if I raise it at some point, I mean, I can always leave it down and the data would be valid for the most part, probably up to here. But if I were to alter it, you can see that there's a certain amount of time from when I change TOD to the time that it actually disappears. So again, this stuff isn't instantaneous. It takes some time. Okay. So again, if I want to operate my system faster, right, I would need to make sure, well, first of all, I need to make sure I'm reading my data at this particular interval of time. Again, if I move chip select further down here before I change it, I'll obviously increase this window here. But if I can't meet the timing, I again have two options: either get a faster memory device or slow down my system, right? And usually slowing down the system is the better option. Again, you have to kind of really look at what your application is. Do I need my system to be operating at whatever speed it is? Not every electronic system has to operate at maximum speed. Usually we usually pick a speed that's, you know, just right for the application, and that's good. Because again, the faster transitions or the faster clock means more power consumption. And I obviously need better parts to keep up with that. So again, these timing values will change based on manufacturer. Again, this is legacy memory. There weren't a lot of standards back then. Now, if I go to for the write operation, it's very similar. I have my access time here. Here we have address setup because the write is different. It's not access time. It's the time that it takes, you know, that my address has to be valid for in a certain amount of time. Then, of course, I have to assert my read and write signals at some point here. Again, they could probably be asserted at the same time, but we usually want to wait a little bit for our signals to settle, right? If we have a little glitch in our address, it could end up writing to the wrong place in memory. I already did drop the last Monday when we were doing the testing. So what results you guys are seeing online right now through the iClicker system is actually valid for the most part. Anyway, so once we assert the write signal, we have so much time to present the data valid. So this is me presenting the data to the memory. So I have to make sure that the signal I'm giving it is valid between these points in time. So if I were to raise the read-write signal at some point, this will be valid for, you know, whatever this is, DH, data hold time. And the setup time is saying, well, once the data has to be here so long before I assert the signal before it captures it. And of course, TWC is the write cycle time. So this is the amount of time it takes to actually perform the whole write. What if you answered all correctly? Then you should have 100%, I think. Okay. You guys should check your results later. If it's not showing 100%, well, I'll take a look at it. Maybe it's just the way it shows the data, but I'm pretty sure it's quite correct, hopefully. Okay, it's 11:25. I should probably stop there. So again, at 1 o'clock, I'll should have the lab posted, and I'll have you guys kind of like look it over and see if there's any particular issues. And again, you guys can possibly start working on it, or I might do a lecture. We'll see how it goes. So again, just sign back in around 1 o'clock, and we'll see what happens. Are we going to be using remote access for the lab? No, the lab is simply like an assignment. It's not anything special. I give you an assignment, you just do it, and you submit the file separately. No particular hardware is needed. Is it handwritten? No, you enter the results in a text file. So you return everything digitally. So you'll upload me a text file on Blackboard. I'll have those instructions in the assignment. Okay, so I will see you guys at 1 o'clock then.